Okay, so we've now been through two parts of the week 7 RScript, and I'm just clearing up my console here so that you don't see everything that we've just finished doing. And now what I'm going to walk you through is the portion of the week 7 RScript where we were looking at the chi-squared contingency test. Now, in R and in other sources, this is also sometimes called the test of independence. Particularly in R, this is called the chi-squared test of independence. And what you'll find is that this is the most commonly used test when you are looking for an association between two categorical variables. So the example that we're going to be looking at here is example 9.4 from your textbook. And while you guys don't have access to this, I actually have access to files from the textbook. Now, you'll see one thing that has probably happened to you guys at some point or another. If you look here, it's telling me that it cannot open my file. And the reason that it cannot open up my file is because if you check up here in my working directory, I have shut down my computer since the last time I ran R, so I am in fact not in my correct working directory. So to verify that, I can just run this line of code here for get WD, get working directory, and you need to have those open and close parentheses there, and you see that I am not where I want to be because this is in fact where my R working directory and also therefore all of my R documents are. Okay, so now that we've taken care of that, we will come back here to the chi-square contingency test. And so like I was saying, this is from example 9.4 in your textbook, and we're looking at some data here on birds and whether or not they were eaten, if they had a high, light, or uninfected status here. So you can see that the format in which this CSV file, which is just data that your textbook had for this example, you can see this is not really the correct format for how we want to set up a contingency table. Okay? So if we look here, call names, I'm just calling up these column names because, as you know, we have to make sure if we are referring specifically to these column names, we have to ensure that we are referring to them exactly as they are written. This means any sort of capitalization, if we have any spaces or periods or hyphens, if we have any misspellings, any of that, we have to always make sure that we're referring exactly to the column name. Okay, so we have this information, okay, and I have loaded this information into the table. Okay. There are a few different ways that you can bring data in to R. And in this section of the week 7 code, that's what I was trying to do, is go through and highlight a couple of these different ways, just so that when you are deciding how to get your data into R, you have some options. Okay? So right here, we can very easily, I'll just enter a couple of empty rows here so that it's easier to see. Okay, we could say row 1 is 1, 10, and 37. The C here is going to combine these three numbers that are separated by the commas, and I'm going to tell it a row 2. If you look in your textbook, you will see that these are the rows as they go across, row 1 and row 2. Now, I'm simply going to call my new data table, data.table, and I'm using an rbind function here that stands for row bind, and I'm binding these two rows together. Okay, so if we now call this up, here is my data.table, and I can tell it what I want the column names to be, and I can also tell it what I want the row names to be, and then if I call data table up again, we see that we have a perfectly reproduced version of the table that you find in your textbook. Okay. Now, what I'd like to show you here, there is an alternate way that you could build this matrix. And I'm showing you this alternate way because sometimes we have data in a format that is not exactly the right format that we need it in. So if we look back, okay, we look back here at birdworms. Okay, I've already called this up before, but this is just to show you again what this looks like. Okay, so what we want to have is a table that looks like this table right here. Okay, where the numbers go across 1, 10, 37, and then row 2, 49, 35, and 9. But what we have these numbers going down in a column, but they don't go across. We don't have 1, 10, 37. We have 1, 49, 10, 35. And if you look at that arrangement, and we look in our table the way we want this to show up, the 1 is here, and then 49, we drop down 1 cell. Then if we go over and up, we have 10 in that cell, 35 in the cell beneath it. Okay, so you can start to see what the pattern here is. So the way that we can build this, and I'm calling this alt-way data table because it is an alternate way that you can make the same data table. Alt-way data table is matrix. Matrix here is going to make what I am putting in parentheses into a matrix, which, remember, a matrix is simply rows and columns of data. So I am making a matrix, and I want to look at birdworms, and because this is where I have this data loaded in. Birdworms, and I want to use the string character, that little money sign, and frequency. Okay, frequency, because this is the column that I want to be looking in. Now, just for clarity, right here I am referring to this column, or, well, I can actually just select that column. I'm referring to this frequency column as birdworms, money sign, frequency. I could also refer to the same thing using brackets. So using birdworms, bracket, comma for all rows, and 3 for the third column here. Okay. And the next thing that we see by row equals false. All right, now what by row will do is it will take these numbers and it will fill the rows. We also need another piece of information here. We've said n row, this is number of rows, is 2. So number of rows is 2. It knows that there are 6 numbers here. So it knows that it needs to put 3 numbers in each of 2 rows. So by saying by row equals false, it means it's going to fill up these cells by columns. So it's going to go 1, then it's going to move down and put the 49 because that's the second number. Then it's going to move over to the top and it's going to fill in this column with the 10 and the 35. If we said by row equals true, then it would fill from left to right, completely filling up a row, and then it would go to the second row and fill that one completely. Okay, so it all depends what your input is to dictate exactly how you need to specify this command if you choose to build your table this way. All right, so I've now told it to do that, and if we type in here alt-way data table, we see that we have our numbers. Our numbers are in there correctly, but we don't have any row or column names. So I'm simply going to repeat very similar lines of code to what we ran before, where I specified the row names. And then we'll look here at our alt-way data table. Okay. And if we stick some column names on there as well. All right, now perfectly reproduced. So now data.table, which we see up here, okay, data.table, and alt-way data.table are exactly the same thing. Okay. Now just for the sake of completion, there is yet another way that I'd like to show you how to enter your data. And this way, the way that I have it set up right now, it's using the default in which any sort of white space are closets. So more than 2 spaces, commas, tabs, anything like that should result in your elements being split. Split into different cells is what I mean here. Okay, so it doesn't really look like it over here in the R console, but over in the RScript, all of these elements here that make up, say, this table are all nice and neatly spaced out and tabbed. Okay, now the next line of code that I'm going to run, I'm defining what alt-way to data table is, because this is the second alternate way that we can build a data table. Okay, as matrix, because this is going to make a matrix, it's using a function called read.table, and it has to use this text connection function associated with input. Now input is what I just typed in up here. This does not have to be called input, but whatever you call it here, you have to put that name right here. Okay? Header equals true, because I did enter header rows, and where the row names go, well, the row names go in 1. Okay, so that is how we do that. And if we now call up alt-way to data table, we can see yet again that we have perfectly reproduced this table. Now, one caveat that I have noticed is that particularly if you are taking RScript that I wrote, like in this week 7 RScript tutorial, and you are trying to run it on a PC, or also if you're trying to run it on a Mac that is very different than the configuration of my Mac, then people seem to be having some trouble with my spaces and tabs lining up just perfectly to give them the exact same result. Okay? I simply mention that to you so that you are aware that it is a potential issue. If you are using this read.table command and you are building your table in the same way that I just did, if that works best for you, then you could actually go and look up the help for read.table, and you can see that you can also specify alternate ways of separating your elements that go into your table. Okay, so this is a way that you could do it, but back to the test, okay, because the point here, we are learning how to run these contingency tests. All right, so in order to run this, okay, now we are going to run this test, and remember, the contingency test, this is really just a special case of the chi-square test. So again, we're going to use that same chi-square.test, and I'm using data.table. I could run this on any of the matrices that we just created. I just chose the first one. Okay, so here we have our result. Okay, so we get our x, our chi-square value of 69.756, 2 degrees of freedom, and a p-value of 7.12 times 10 to the negative 16, so way, way, way less than the typical 0.05 significance level. Remember also that you can save these results. So here I'm just storing these results in a variable name called results2. And if I do that, I can now call this back up whenever I feel like it. And also, interesting and fun, and a good source for questions as well, also a nice way for you to satisfy your own curiosity that R is actually calculating things the same way that you would be doing it by hand if you had to calculate out all those elements. You can call up the expected values from this chi-square test. Okay, so if we do that, okay, we can see what our expected values would be. Okay, we know that we have a very highly significant test here, but why is it so significant? Well, if we look at what we observed, so of the uninfected cases, 1 we see eaten by birds, and 49 not eaten by birds. Well, what was expected? Well, here, if we look at the uninfected, 17 were expected to be eaten by birds, and about 33 were expected to be not eaten by birds. So if you follow through and look at each one of these values, you can see that they do actually all differ by quite a bit. So we see that there is a significant relationship between these two variables here. All right, so one of the things that you may be called on to do, depending on your experimental design or depending on the experimental design in a potential question, might be following up on these tests. So we have a very highly significant result here, but we don't exactly know what that means. Okay, so I'll run you through here post-hoc test on contingency tables. Now, I do want you to harken back and remember the portion in the notes as well as in lecture when I talked to you a little bit about these post-hoc tests. Remember that you should only do post-hoc tests if your initial test shows a significant result. And the reason why we don't want to do a bunch of tests when there's no real call for it is because remember that that alpha level, typically we're working at 0.05 as our alpha level. Well, alpha also represents the probability of making a type 1 error. Okay, making a type 1 error that is a false positive, so this would be rejecting the null hypothesis when we really should not be rejecting the null hypothesis because the null is true. So if you do follow up post-hoc tests after you've had a non-significant initial test, you could simply by chance, there is a 0.05 probability that you will reject the null hypothesis even though it is true. And since you've already shown that there's no significant result, then you wouldn't do follow-up tests. However, in this case, we do have a very significant result, and we might want to know exactly which things differ. All right, so we're only going to do those post-hoc tests if there is a significant result from the initial test. Also, remember if you have a 2x2 table, you don't need any post-hoc tests because with a 2x2 table, you already know what differs. All right, so to run these post-hoc tests most easily, you have to install another package. And I've already installed this package, so I'm not going to actually run the line of code to install it. I'll put a hashtag right before it. It would look exactly like this, only without the hashtag if you haven't done this. But seeing as this is something that we did in lab, I know that everybody has done this by now. All right, so here I'm just loading in this package because I'm not positive if it's been loaded yet. And it's very simple, actually. It's this one line of code here. This is all that we need to run, okay, to get all of our post-hoc comparison tests for this contingency table. And there's a couple different elements here to this argument. I'll go ahead and enter a couple blank lines here just so that we can look at this in a little bit more depth. All right, so what we have to call up every time is pairwise nominal independence test. Data.table, because that is where my data happen to be. This will be called whatever you have called your data. Compare equals call because I'm comparing the columns here. If you look up here, my columns are uninfected, lightly infected, and highly infected, and I want to compare these columns to each other. Okay. And then we have a couple different tests that we could have done for us here. Notice this says Fisher equals false, G-test equals false, chi-square equals true. We could very easily get F-test and a G-test out of this, but because we're not really focusing on those tests in this course, we're just going to say false for those. But do remember that this is a way that you can get these tests as well. And feel free to experiment and play around with it a little as well, because if you have different data going in to this that is better suited for Fisher's test or g-test or chi-squared, you will see the cases where they start to deviate from one another, and you'll also see many, many cases where, honestly, they really do just give you very similar results. So to keep it as simple as possible, we're going to focus on that chi-square test. All right, there's one more element that you see here, method equals Bonferroni. Now, if you look at the help for pairwise nominal independence, you will see that there are many different methods that could be written in here. I've chosen Bonferroni because Bonferroni is a very conservative method of correcting. And just to clarify exactly what I mean by comparing, we're doing multiple tests here. So one way that we can abate this problem of type 1 error is to adjust our p-value. Because if we make an adjustment to our p-value that takes our p-value even further away from our significance level, if it makes our p-value higher, it's going to make it more difficult to reject the null hypothesis. So when you're doing multiple tests, you will adjust your p-value. So this output that we have here, what it's telling us is which comparison we're looking at. So here we're looking at uninfected versus lightly infected. And we get a p-value for the chi-square test. This is the unadjusted, uncorrected chi-square p-value. This is exactly what you would get if you had set up a 2x2 table and you were simply comparing these two things. So if we look here, if we got rid of the highly infected and you just set up this portion here, the eaten by birds, uninfected column, lightly infected column, but got rid of all of this. Okay, that's the p-value that you would get. But we don't have to break our data into all of these small 2x2 chunks because we have the ability with this pairwise nominal independence test to get that adjusted chi-square value. Okay, so if I just ask you for a p-value from one of these post-hoc tests and I don't specify if I want corrected or uncorrected, I will be talking about the corrected value. And you can always make sure just that we're on the same page. If it's a lecture exam, you would simply write down this is the adjusted value or this is the non-adjusted value if that's what you're giving me. And you can also leave me a note too if it's something that you are doing on a lab exam, or you could just raise your hand, come to the front, and ask me if I haven't specifically told you which value that I'm looking for. Okay, but here we have these values, we have our three different comparisons. Okay, now the other thing that I wanted you to do was simply to compare. Okay, so we talked about all the different elements that went in to that. Now if we run this other line of code here, notice the only difference that I put is instead of compare call here, I said compare row. And when you compare row, you see this is not really what it is we were looking for because this is only going to be comparing eaten by birds by not eaten by birds. Okay, so that's not exactly what we were aiming for here in these comparisons. Okay, and this line of code is simply pointing out to you that the whole thing I was talking about with the Fisher, the g-test, and the chi-square test, if we say false, it's not going to give us those results. Okay, all right, so that right there summarizes the contingency table tests that I'm really going to be asking of you to do. One other thing that I'll just sort of go through and highlight at the end of this one here is just doing this Fisher exact test. And I talked a little bit about it in the notes, you've read about it, and because the chapter talks about the Fisher test quite a bit, I did want to include it here in this tutorial for you. Really the reason that I'm including this F-test is because it gives very similar results to the chi-square test, but it is also incredibly easy one for you to calculate if you were doing it by hand. Usually people think of the Fisher test as being only for 2x2 tables. And if you were doing this by hand, then a 2x2 table, that's really where you have nice easy math and where it would make sense. But in R, this Fisher exact test has been extended, so it will work with much larger tables as well. Just as long as your frequencies that you have in all of those different cells aren't too big. Okay, now, again, remember this is just putting your variance values one on top of the other, and if you were running this Fisher test here, it is easy as just typing fisher.test. Okay, so right here, these would be the results from your test. We see that it is not the same exact value, but it is a value that is very much in the same ballpark as the value that we got looking at the same data. Okay, so I'm not really going to ask you to be running Fisher exact tests, but since you will see them in your future, I just wanted to show you what that actually looks like. Okay, and then I also walked you through the example that was in the notes on blue line. So I'll just walk you through that real quickly here. Okay, so here I am inputting the data using this table format. Okay, so here we've got males and females, and we were looking at 4 different causes of death, and we want to know if these different causes of death are going to differ significantly across the sexes. Okay, so again, I could build this the same way that I've shown you before with row 1, row 2, binding those rows together, and then entering in some column and row names. Okay, so we can very quickly and easily run our chi-square test, and we see a p-value of 0.00808. Okay, notice that we didn't have to do all of those steps that we did earlier when we were looking at that very first example and we calculated out those expected numbers. When you read through this example in the notes, you see that you do have to calculate out these values if you are doing this by hand. But if you are using R, you don't have to calculate out these values by hand. Also, you can store these results. So here now we can look at the expected values. We could call back up our p-value if we wanted to. It's actually not called p, it's called p-value. Okay, so we can call that up. Okay, and just to demonstrate that we get very similar results and we can easily run this Fisher test, if we do that, we see that also gives us very similar results. And because we've already loaded in this R companion, we can also very quickly get all of these post-hoc comparison tests. So when the notes went through and it explained to you how you would break this table down into all of the different 2x2 comparisons. Okay, here we don't have to actually do that because R will just do it for us. Alright, so now you have all of these results. How do you actually interpret them? Alright, well, because we had that initial significant result for our chi-square test, we reject the null hypothesis that there is no difference. We conclude that there must be a difference between the sexes in the rates at which they're dying of these different causes. But we need some post-hoc tests to compare the different causes of death. Okay, so looking at these different causes of death, looking at these results, we see that there are significant post-hoc results for cardiac versus stroke, for stroke versus cancer, and for stroke versus other when we're looking at the unadjusted p-values. But you see that there are 6 different tests that were done here. So these p-values are being adjusted using the Bonferroni method here, which is a very conservative method. And if we look at the p-adjusted, the adjusted chi-square values, we see that all of those p-values get bigger. Okay, they get farther away from 0.05. So we have less things that shake out as significant. Okay, looking at those unadjusted values, we have a pretty good idea that stroke seems to be different than the other causes of death because we keep seeing that pop up, cardiac versus stroke, stroke versus cancer, stroke versus other. But then it's when we look at those corrected p-values, we see that the strict correction factor Bonferroni is altering these p-values, it's adjusting them so that we have a single test that shows out as significantly different here, and that is the difference between cardiac and stroke. So there's a significant difference between men and women and the rate at which they die of heart issues versus strokes. That's what we could say about these data here. All right, so hopefully for those of you that are a bit more visual learners here, and for those of you that it helps to sort of walk through and talk through the examples, this has been helpful. In the next installment, I will go through some of the t-tests.